Hello guys, and welcome to another video. In this video we're going to be dealing with our axial and combined moment or asymmetrical moment problem. And in this problem right here we're trying to find the stress at point A and B, and we're going to be using our regular stress equation with our moment in Z, moment in I, moment in Y, moment of inertia in Y, but also including our axial and our axial loading, which is that P over A equation. So it's also asking where the neutral axis intersects AB, so we're going to have to find that at some point too. But we do know that we are going to for sure need to find our moment of inertia for this cross section in both our axes, in our IY and our IZ. We do know our regular moment of inertia equation, which is that, and we're going to have to find our moment of inertia for IZ and IY. So this is here, right? For IZ and IY. I'm switching everything back to meters because that's going to be helpful for us in the future. Pause this and then solve and then find your answer and then come back to this video real quick. These are the numbers I found for moment of inertia in the Z direction, and it's easy for me to remember which way the Z and which one the Y is by looking at the Z axis and then taking my base as the same perpendicular, parallel to the Z axis. So for our IZ, we're going to be taking 75 millimeters as our base, and then looking at our IA value going this way. So always moment of inertia of the Z, take your base parallel. Right? Also, let's take care of that axial and area calculations. We know we're going to use those. So for axials, they all add up. It's straightforward. And areas, just take the areas and then subtract them, and we can do that because the centroid is in the centroid of both these squares are in the same place. So we can get those numbers, and this one, switch it back up to newtons. It would be beneficial for us later. It's not staying kilonewtons to make our numbers nice. Let's do our moments. Moments in Z, moments in Y. We do know that those are gonna be in our cross section, and let's denote what our positive moment is and what our positive Y moment is. A way that I like to look at this is, I'm trying to find the moment at Z. I'm imagining puncturing through the Z axis and then seeing it from this side, right? So we have a 14 kilonewtons this way and 228 kilonewtons from the bottom. So that's how I visualize it, right? So we have a Y going to the top, and then our X pointing out to the outside. Same deal with the Y, but we're going to be looking downward. So our Z axis appears to be coming down like this if we're looking at it from the top, right? And here I added my 28 and my 14. I hope I did that correctly. And we have our distance, right? And remember, moment is force times distance, and that way we can find it with our axial loading, right? With those numbers plugged in, just making sure we got our signs correct. This is 14 kilonewtons going this way in our clockwise direction, but counterclockwise is positive. This is going to be a negative 1400 newtons, right? Because we're switching it to newtons, and then we're making this number like this. All right, so we got our two answers for this, and we got a negative my and a positive mz. So what does that actually mean? What does that look like, right? So I like to draw a little picture. We know that we got a positive mz moment, which is going to be a positive moment going this way. Remember the right hand rule: curl your fingers towards the arrow in the direction of movement, and your thumb is going to be pointing to the positive z. Same with my. We got a negative my, so our thumbs are going to be pointing down, and then the curl is going to be going this way. So this is what our actual moment looks like. Not to scale, but get a rough idea, right? Right here we have a lot of information. We can basically plug it back in to our stress equation, our governing equation, and remember that our equation looks like this, right? We have a P over A. Not right now, not right now. We have a P over A, which is our axial loading, what made this problem weird, right? And putting everything into the correct units that we like, you know, we have our mz over I is negative, always mz over I is negative, and ya and yb are going to be different in this problem, and it's important to know what direction we're going in, and we can look at that from looking at our drawing. Y, the positive y is going up, so our b must be positive, and our a is going in the negative y direction. So that will change your answer. So we got to make sure that we have the correct signs there, right? And going everything putting it in kilonewtons, everything putting it in newtons and meters to make sure that we're in our correct unit. So newtons and meters, our stress is going to be in pascals, right? If we have anything that isn't exactly anything that isn't a nice small number, we're going to be switching it to megapascals, kilopascals, gigapascals, all like that, right? So these are our two numbers that we get while we plug in this. I plug it in several times until I get some numbers that are reasonable, or, you know. These seem to be all right. Megapascals, because I did have a 10 to the 6th. So this number is nicer to read, and it translates and communicates clearly. So we were also asked for the neutral angle. We know that the neutral angle is 0 when it is, neutral angle is 0. Stress is 0 and neutral angle. So in order to find where it is, I think about it as finding where the y of the neutral angle is. So putting it in this equation that we know, this is how I kind of thought about it. You got our P over A, mz over iz, but we have our y of our neutral angle that we're trying to find, and then our z of our neutral angle, which we're not really looking for. And so what we can do from here is, once we've rearranged it and we have this, we can start, these are the numbers I came up with our equation like this. Trying to figure out the numbers that we had, and putting it all in here, making sure that we have our correct units, correct signs, and this way we're going to be getting a number that works for us. Once you plug that in, we're going to be getting our answer in meters. And because the problem originally was given to us in millimeters, we're going to have to switch it back, because it makes sense. If they're giving you millimeters, you give them back millimeters, right? Here we have this translated. I'm going to draw a little picture because we're measuring from the positive y, you know. But it makes either sense, counting it negative from the B or positive from the A. So I just left it at 94 millimeters above the A by just measuring what this distance was. Hope that was helpful, and I hope I didn't take too long rambling on, but I feel like this problem is important to understand where the signs come from and how to get the moments, how to know what to do with axial loadings, and it's a good practice problem. All right, take care, guys.